Can you hear me? Okay. So I'm going to illustrate how to analyze demographic and location data. And as I say, the goal is to create a short list of locations which are deemed valuable to open a new Japanese restaurant in the city of Toronto. So we know in Toronto there's already a lot of restaurants and therefore a high competition in the restaurant business. And the other things when it comes to the right location for restaurant, the one that has a high foot and car traffic makes sense. And for this case, because we are creating a list for Japanese restaurant, it makes sense to target middle class and above. So the criteria for our valuable location is basically income above. We're targeting location with income above 70,000. We're looking for location with high population density as well as high number of business, at least 25, because the more business you have, the more it's going to generate foot and car traffic, especially when they are popular and more people are going to those businesses. And having more business is not worth it if the population per restaurant is low, because when you have population per restaurant low, that means you have high competition. So we have to balance it. And for this case, I set it to 2,200. That way, it's a margin of safety. So in case we don't have enough information, the things that we didn't take into consideration, that's probably going to be enough. So we need data to find information that can help us to make a decision. And for this case, we are using 4 different kinds of data. The first one is the data from the census, which include the demographic data, such as age, gender, average income for each neighborhood. But we are going to retrieve information about most popular venue in each of the location, and we're going to use the postal code. So we need postal code to associate postal code with each of the neighborhoods. So that's the Wikipedia information for. And then you also need the geolocation that will help us to retrieve those information from Foursquare. So here's a sample of the data that I obtained from Open Data Toronto for 2016 census. And you can see here, number 1, there's columns for each neighborhood. For example, Annex is one of the neighborhoods, and see in the column. And then we have additional information such as the city of Toronto, ID category, which we don't need in this case. And there's about 2,400, which you can see here, variable for each of the neighborhood, but we only need 4. So to get to that point, to get to what you see here and below, there are some of the things that were done, including the step above, to remove some of the columns that were getting away into us getting the right kind of columns, and then transpose the matrix and extract the column. After that, the check was done to check if the variable had right data types, and it was found that the variable didn't have the right data type. Then they were converted into float and integer as feet. For example, population was converted into integer, while land area was converted into float. After that, another check was done to verify if the data makes sense. So there are values for City of Toronto that were provided in the data sheet. So for example, if by adding all the population for individual neighborhood, I was supposed to get the same value as the one that was provided for the City of Toronto. And that was the case. The same case for land area. When I sum it, it was the same number. Let's say it was the sum of population over sum of land area. And that was correct. But for income, it wasn't the case. So for example here, if you look at Annex, the income is $792 after taxes. That's the average household income after tax, $792. But what is listed on their website is $203 average family income. Average family income is supposed to be higher than household value. So in that case, I realized that the value is higher by at least factor of 4. I calculated the weighted average, the value for Toronto using weighted average because they're not equally populated. And I got 400,000, higher by factor of 4.9. And then I did this one. The mean is actually not the real, I got 351,000. And the actual one that was provided is 81,000. So when I divided that was like a factor of 4.31. So I decided to use this one as opposed to 4.9 so that I can have more location remain once I apply one of the filter. And then at the end, if I get bad results, then look for another alternative. So now we have those data. We need the postal code that can be associated with them. And this information was scrapped from Wikipedia using Beautiful Soup. And from that, the HTML table contents were transformed into a nice data frame. And then from that, the not assigned borough and neighborhood were removed. The thing about this data, there are like 211 neighborhood left after I clean up. Having said that, I made a wrong assumption assuming that this neighborhood's name that existed before they came up with this list of designated, 140 designated neighborhood, they are different. And therefore, if I merge them, I won't get back most of the neighborhood. So I decided to sort it up, sorted the list, because they had another list that has both the designated list of neighborhood, 140, that City of Toronto came up, together with the actual neighborhood that are corresponding to that, those neighborhoods. So I used that to edit it, and after editing it, when I made this time, I got at least 95% of the neighborhoods, and that is what I continue with. So at this point, you see the 3 call letters. Even here in Edmonton, you can have several neighborhoods sharing those. So in this case, we want the postal code to be unique because we're going to retrieve information on those postal code. To do that, we have to aggregate data in such a way that we have unique postal code. So for neighborhoods, the name were combined together, separated by comma. For population, it was a sum of the population. For land area, it was the sum of land area. And for density, it was the sum of population over sum of the land area. And for average income, it was weighted average income. So it was done in several steps. And then, yeah. So if I go back here, you see the sum location. They have income below 70,000. And one of the criteria for available location is location with income above 70,000. So to get to that, the filter is applied here to remove those locations that don't meet that particular criteria. And after that, the data for geolocation are retrieved and are combined together with this other data that kind of meet criteria for valuable location in respect to the income. So using this latitude and longitude, you can also visualize them on map, like you see where those locations are in Toronto, right here. And this was done using Folium. And those markers for different locations were superimposed here. So with the longitude and latitude, you can also use Foursquare to get the top 100 most common venue based on their popularity. And this was done around radius of 1 kilometer. I try lower values such as as low as 500 and as high as 2 kilometers, and 1 kilometer made sense for this case. And the response for this case is JSON response, and from that, the data frame was created using only the values that we're interested in. And for this case, we're interested with venue, latitude, longitude, name, category, and the name. And here is an example of those information. You can see their name, like for example, Summerhill Market, and their venue longitude and latitude is different from that original one that we use on the left side. So from that, you can look at which are the top, most popular venue category. And here you can see coffee shop, which is not surprising, cafe, they're among the top one, and park and other restaurant, they're also among the top one. You can also take a look at the top 10 most popular restaurant. And here, Italian restaurant is at the very top, but sushi restaurant, which is a Japanese cuisine and Japanese restaurant, are number 3 and 5 respectively. So we have venue information, and from there we can get number, like information that we need that can help us to make the choice easy of this location. So, for example, from that venue information, I can calculate the number of business that are there in that location. I can also calculate the number of Japanese restaurants from that location, as well as the number of restaurants, including the number of Japanese restaurants. And using that number of restaurants and population, I can get a population per restaurant. But there are some cases Foursquare didn't return any restaurant. For example, St. Andrew Winfield, it only returned 4 out of 130 requests. And I look at them, 3 of them were park. At the beginning, I thought maybe I did something with my assumption, but I look at them there. 3 of them were park. And I don't know whether there isn't any business or it has to do with how this information are collected. So for those cases, like if you divide any number by 0, you get infinity. But the maximum we can have is the whole population. For this case, if you don't have any restaurant, the population per restaurant will be equal to the actual population. So I have these new features that were derived from that venue information. Like before I create a cluster, I need first to normalize, because if you look at the range of this number, the unit is so different. So I need to normalize to remove any kind of bias. And then I'm checking how variables are correlated, because you don't want to create a cluster with variables which are correlated. So for this case, I use PCA to create a new feature out of this that are correlated. So you can see here, when I look at them, for example, number of restaurants and number of business, they are highly correlated. 0.88, which is approximately 0.9. And the same thing for number of restaurants, for some reason, and number of Japanese restaurants, they are also highly correlated, 0.82. And you can see there on the density side, if you look at number of restaurants, number of Japanese, and number of business, they're like moderate correlated. So you can use, for this case, as I say, I normalize the data, and then I apply PCA to reduce the number of features from 8 to 5. And the new features, you can see the correlation is approximately equal to 0. Using those new features, 9 clusters were created of locations. And most of the clusters have more than one location. For example, cluster 0 has 5, while cluster 7 and 8, they're the only one who have one location each. So, I mean, from this map, we can't tell much, but there is detailed information from here. So from here, you can see cluster number 0. I'm just going to focus on the ones with high number of business, because those are the ones that will end up having high foot and car traffic. So cluster number 0, cluster number 5, and cluster number 7 and 8 at the bottom, those are the ones with high number of business. But cluster number 0, the income is between 100 and 170, while cluster number 5, the population per restaurant is on the low side, like below 1,200. So this location in this cluster, they have high number of business, but they have a lot of competition at the same time. Cluster number 7 and 8, they have the highest number of Japanese restaurants also, in addition to high number of business. But cluster number 8 has the highest population density of all the locations, probably in Toronto, the whole of Toronto, compared to other locations. Cluster number 7, if you look on the population at the very bottom, it's higher, it's on the highest side. So here at the top we have a list of locations where, yes, they have a high number of business and therefore, like, which are more popular and people are going to them, and therefore high foot and car traffic those locations have. But there is a lot, population per restaurant is lower, and therefore there's a lot of competition. Even if you look at the one which have a higher value, 1707, Lansing Westgate, it has 14 Japanese restaurants already. So that's like you have more competition there, too much competition. On the below here, I have a list of the location which meet criteria for available location. And you can see most of these locations are from cluster 0, right? And their population per restaurant is above 2,500. And their population density is also about 5,500. For the one from cluster 1, it also met a criteria because it has a number of business, 34 number of business, and we set a criteria to 25. And the income, even though it's just borderline, is still above 70. So with more information, you can decide whether to raise this threshold to more, like 40, or keep it at the same level. So here I went to look for median family income. Remember the other one I had to do some scaling. So this one, whatever that I obtained from their site, I just put it there. And still, even Don Valley is still around that much. And most of those made like criteria for our valuable location. So what I can say, like, in the process, yes, I had some challenges with data, and it would be nice to have more reliable data that we can rely on in the long run. And if you need to do like further analysis, you need more data, of course. You need more data that will tell you more about the environment, accessibility of that particular location, parking space, the number of parking space, crime rate, that kind of thing, as well as the data that will help you with your cost analysis. So that's all. And if you have any question, feel free to ask. And here I have a link on GitHub for the notebook. So there's more detail there.